Please welcome Jace Browning, who's going to be talking about synchronizing objects to YAML using Black Magic.
So lately I've been running into many situations that involve loading program configuration or data at runtime. And after exploring many options, I discovered that utilizing version control for storage and retrieval offers some really nice benefits. I also opted for YAML as the file format for its human friendliness and pretty decent compatibility with version control. I began to notice some common patterns in libraries and tools I was writing around this object serialization and data loading. And eventually these patterns got extracted into another library that I called YORM. This talk is an overview of this library and some of the less common parts of Python I've utilized along the way. Hi, I'm Jace. Professionally, I focus on DevOps, quality assurance, and testing. In my free time, I write a lot of Python code for projects that interest me. You can find me online at GitHub and Twitter as Jace Browning. So let's begin. I'm going to start with a quick demo of this library, followed by going over the specific requirements I had that led me to some of the choices I made. Then I hope to convince you that storing YAML files in version control is a good idea for managing program configuration. After that, I'll walk through a list of the Python features I explored in the process of building this library. And finally, I'll go through just a full overview of the library and some real-world use cases that I'm doing currently where this library becomes useful. So this is sort of the hello world of YORM. We take a class. Here we have a student class with some attributes that we define at initialization. And we have a directory in our file system, and it's empty. If we add 2 lines of code that we import from YORM, we're defining attributes that we'd like to map to file, and we're providing a pattern to sync instances of this class to the file system. At this point, the file system is still empty. We're going to be we're going to group students by the school they go to, and then we're going to key them off of their student number, which could be the same for multiple schools. So now we just create some instances of these students in our REPL. And on the file system, suddenly we have a directory called students. And inside of that, there's a subdirectory called GVSU, and that has 2 YAML files in it. Those are the 2 students we created. If we cat one of those students, we can see it's a YAML file, and it has the attributes that we mapped earlier. If we modify one of these YAML files, so here we're echoing in a new GPA and a new attribute that didn't exist before, expelled, those are both immediately available on the object in our REPL. So I had a few goals for this library that led to the final storage choices and some of the API decisions. But first I want to explain what I mean when I say program configuration and program data. Program configuration, these are things I'm thinking of here is like system setup, maybe user-defined options that they're going to save for later, and program data more like seeded default values or a persistence model, or even something you'd use maybe in test fixtures. When working with this type of data, ideally I'd like it to be updated automatically whenever it changes, stored in a human editable format, work with multiple human editors, either in parallel or offline. And obviously these should be compatible with built-in Python types. Some of the alternatives I've looked at, you've got your database ORMs that typically are using the active record pattern. I didn't really like this for my use because it requires you to use their types. Your code is going to be very tied to the way that ORM works. And I know it's a bit un-Pythonic of me, but I never really liked all the .save calls and things like that. For this, I'd really just wanted it to happen automatically and be pretty invisible. There's also There's serialization libraries in Python. There's Marshall, Pickle, Shelve. These really aren't intended for human editing. It's text, but if you are going to try to do stuff by hand, you're probably just going to break things. You're not going to be able to diff or merge in any reasonable fashion. And then I also looked at just using JSON and just maybe storing JSON files and working with them as straight Python dictionaries. This is the closest to what I ended up with, but I wanted to have a little nicer interface than just messing with dictionaries. From the API side of things, I wanted the library to require limited modification if you want to use this in your code, and work automatically by default with an option to do it explicitly. Be able to add new attributes at runtime, so when you're working in a shell or something like that, and also support custom user types for whatever domain you're in. So here's the way it works today. I chose YAML and stored in version control. I'm going with the subset of YAML that's compatible with JSON. And then the YAML files are created in such a way that they're optimized for human editing and diffing and storage in version control. There's two ways to enable this synchronization on an object. You can use the class decorator that you saw in the hello world example, or you can use the same function to sync an existing instance to a specific path. So this is the class decorator, and that's the function. In both of these cases, the student instance is now synchronized to a particular file. The way this synchronization works, when you go to save, when the library goes to save attributes, all the mapped attributes are collected into a dictionary of just built-in Python types, so that these can be dumped to YAML text directly when the YAML is written to a file. In YORM, this process is called storing. And then once that's stored to file, the keys in the dictionary, in the YAML dictionary, are just the names of the attributes, sorted alphabetically, so you have a consistent format every time it's used. The lists are saved in their expanded form, so even if a list is short, it won't fit on one line. It will always go to multi-line so that your diffs are more consistent. And then strings are, even if string is just a number, it's saved without quotes, just for consistency in editing. And then to reverse this process, the text is read from the file, parsed as YAML into a dictionary, and then the dictionary values are converted back into the original attribute types. So then when you're using the object, it's invisible to you. And this process in YORM is called fetching. So in this case, that first attribute was actually just an integer, so even though you may have typed 3.1, that would be read back in as 3, because you'd expect that to be an integer. Where it says Python 3.4, the unnecessary quotes would be stripped. Serial numbers was expected to be a list of strings, so even though in YAML that's technically a float, that would be converted into a string because that's what you expected it to be. And then white space would be cleaned up as well. When new attributes show up in the YAML file, the type is inferred if it can be. So in this, that would be just inferred as an int, and then that mapped instance is now tracking a new attribute as an integer. So in future modifications to that, it's expected to be an integer, and it'll be coerced into such. This is useful if you're playing around in a REPL or Jupyter Notebook, and you're just sort of playing around with maybe what you want your objects to look like, but you'd also like them to be persisted. And now I'd like to touch on some of the less common parts of Python that I've explored to create this behavior. Some of these things are kind of hacky and likely to have better solution, hence the black magic designator. The first feature is metaclasses. In order for the classes instances attributes to be stored, the class itself needs a way to track which attributes we care about in future instances. So this metaclass, metaclass creates a class. When a class that uses the container meta is created, that class will have a new attribute on it that's initialized to be an empty dictionary. This was necessary to prevent inherited classes from automatically sharing the same mapping, which is what would happen if this was just defined at the class level. Next, class decorators. One of my APIs, I wanted it to be used on top of an existing class. And for this, the class decorator makes sense. This class decorator also takes additional arguments. So we have this outer function that you pass in a mapping, and that then returns the class decorator that's applied and mutates the class object. Being a dynamic language, Python makes monkey patching really easy, if that's good or not. And then one of the behaviors that I needed is to change the initialization behavior in decorated classes. But I also wanted to maintain the old behavior. So the right way to do it is this. You save off your old init method, define a new init, call the old init, and then do whatever else you want. And then you can monkey patch init on your old object to be your new init. Another thing that I was monkey patching was the actual class. So I wanted to dynamically add in a new base class so that I could change the behavior of a bunch of magic methods. So this can actually be done as long as the inheritance tree is still maintained. So it's creating a new class, inserting a new class into the inheritance tree, and then monkey patching the class on that object. This also demonstrates what multiple inheritance looks like in Python. So mapped is both inheriting from mappable and also the original class's object, or object's class. Python's data model defines a number of magic methods, like I talked about before. And these are the methods that Python uses to implement object-oriented programming. The mappable base class from before overrides a few magic methods to create this syncing behavior. The first behavior that I needed to control is what happens when an attribute is modified on an object. And in Python's data model, the dunder set adder method gets called whenever you attempt, whenever you're asking to change the value of an attribute. So the first thing I'm changing here is if I'm setting anything that starts with double underscore, so it's either something that I'm using internally or it's a magic method, I'm just going to return right away. Or I'm going to set it as normal and return, not do anything special. Otherwise, I'm going to look up this mapper attribute that's been added to the object. And if automatic synchronization is enabled, and the attribute that we just set is something we actually care about storing, then we're going to invoke this store method down there. I want to do something similar when attributes are read. This is a bit more complicated. In Python's data model, there's a dunder get adder, but that's not actually the inverse of dunder set adder. Get adder is only called if an attribute lookup fails, and it's sort of a fallback to then dynamically generate an attribute. On the other hand, dunder get attribute is called whenever an attribute is accessed. It's a little tricky to work with this because you can very easily get into an infinite recursion situation. If you ask for any attribute inside of get attribute, it's going to call itself right away. So the first part is if I'm dealing with a magic thing, just return it right away. I don't want to do anything special there. Otherwise, invoke the normal attribute, get attribute behavior to get this object. And if I don't have it, then just remember that it might be missing and I might need to read from file. So if somebody's asking for an attribute that just got added to file, I don't want to raise an attribute error yet because I want to read it from the file and maybe that attribute is there now. So we grab this mapper object and fetch from file if it was missing. And then at this point, if it really is missing, this will raise the attribute error. The final Python feature I want to cover is subclass lookup. To support dynamically added attributes, the converter class can select type at runtime. So all of the converters, integers, and everything is based on, it has this common base class. So if a new attribute has been added to the file, you can actually ask an object to list all of its known subclasses and iterate through that to pick the correct inferred subclass type. Now I'd like to go just over a few more examples that show how all of these pieces work together and then what the library looks like today. So as you saw earlier, there are two main usages of the library. One is you decorate a class. The other is modifying existing instances. But if you want this, but if you want this synchronization to happen more explicitly, you can say auto equals false, and then no files will be created or read until you tell YORM to. If automatic synchronization is enabled, this is happening all the time. But if you manually want to update the mapped file, you can just call YORM.update file. Or you can do the reverse. If automatic synchronization is enabled, the objects will automatically be updated if there's files changed. Or you can call update object, and it will fetch from the file. There's also a helper function that just does both of these things and applies updates in either direction as needed. There's a variety of converters that specify how all these attributes are mapped. YORM has converters for all the built-in types that work as you might expect them to work. There's also base classes for defining container types, so lists and dictionaries. Lists are homogeneous, and all the items share the same converter class. In this example, we've created a list of an object with a config attribute, which is a dictionary in Python. Inside of that, there's a list, there's a key value, and the value is a list of dictionaries. And then each of those is a dictionary with string values. So if any of these change, the nested values will also be updated in the object. And then finally, you can define your own types. So in this example, I want to have a datetime object, and I want that synchronized to file, and I want it to show up in file as a string. So I'm going to extend the string converter, but override the toData, which is defining how we should convert the object into a built-in Python type so that we can dump it to YAML consistently. So we're just going to format the date as a string. And then toValue defines how we would convert that string back into the datetime object to set on the original object. I've been using YORM in a few of my own projects for a while now. The first example is a get submodules replacement, which relies on a read-only configuration file to call out a list of source dependencies that themselves may have source dependencies. So this shows an example of defining your own customs, like sources, which is a list of source dependencies. And even though this project doesn't involve bidirectional synchronization, using YORM still makes the loading and use of the configuration file practically invisible to the parent library. That's the only spot that the config file is loaded, and that's just going to happen implicitly. So when that config object is constructed, that config now has a list of all of those source dependencies. And users of this tool then would be able to write config files, just write in simple YAML as they'd be used to in other tools, without needing to understand how it's used. Like this user is just cloning a few source dependencies for an Xcode project. But they would have no idea, they wouldn't need to know what's happening here. My next example does show YORM being used to bidirectionally sync data. But in this case, the YAML is not going to be stored in version control. It's going to be stored in Dropbox to synchronize the state of programs across multiple computers. So when one computer updates the state of a program, it'll synchronize in Dropbox. And then the other programs that are running using YORM will automatically just see the new state. And then Dropbox essentially takes care of conflicts and determines the winner of whoever has the latest state. My final example using YORM is a data persistence layer in a game API I'm prototyping. By mapping each game's state to its own YAML file, that sample data can then be committed to version control and then shared with other developers, and they can run the games in the exact state that they were left off in. This is really handy in prototyping because I don't even know what attributes are in the game. I don't know exactly how it's going to be stored, but it lets the data travel with the code. So in this, the games are just given unique keys, and all of the game data for each game shows up in a file. So if any of this sounds interesting, how do you get started? YORM requires Python 3.3 or higher, so you can pip3 install it, which will install its single dependency, the PyYAML package. The API is mostly stable, but I'd recommend locking down the minor version until 1.0. The source is available on GitHub, and I'd love for you to check it out and send me some feedback. Thanks. Um, 3.3 is just a good default Python 3 to start with, because that's when there were some issues with like file I/O and just slow stuff. That like 3.3 is the first 3 version you should really start with. I don't think I'm using any like Python 3.3 syntax in this. I don't think I'm doing any yield from or anything like that. So no, just because Python 3, and that's a good place to start.
Metaclass syntax did change between Python 2 and 3. I've written code like this. It's tough to make it compatible with both.
Okay.
Not impossible, though, I don't think. Although I don't think I ever. A question as well. When you are loading attributes that don't appear, you go look at the data file and just automatically load them. Is it smart about when the file changes, and do you watch for file changes, or how do you deal with that?
Yeah, so once it's read from the file once, it's just tracking the modification time. So if you go then read more attributes, it's just seeing the file hasn't changed. So there isn't going to be any I/O at that point. But if you change the file, then it will look at the timestamp and it will read it again.
When you were describing the advanced Python features that you were using, you mentioned metaclasses and monkey patching. It struck me as odd that you're using monkey patching when you're already defining a meta class for the inherited class structure. So can you explain why the monkey patch was needed?
So, so in reality, the meta class isn't actually in there anymore. I ended up that was something I had looked at originally, but I'm not actually using that because I didn't, I realized I didn't need it anymore. But I think there's a lot more work to go in, especially the class monkey patching. That's the scariest part in there, and I mean, it works, but there's probably better ways to do that. Maybe it's all in a meta class or something. But
This looks pretty useful. Would you consider pull requests for backports to Python 2? You wouldn't have to do the work.
Yeah, I don't know. Some of the when you look at 2.3 compatible, using 6 or something, it feels a little impure to me. But if that means people use it, then that would be something to talk about.
Any more questions? Well, thank you very much.
Thank you.